Okay, so this next problem, problem 3, is just a simple plug and chug type problem. We're asked to find the Fourier series for this periodic function f of t with this definition up here. Okay, so it's kind of like a truncated sinusoid, and the idea is that these edges are going to relate to the higher frequencies or higher harmonics in the Fourier series expansion as we saw in class. Okay, first question is, what is the fundamental period? That is fairly straightforward, so T naught equals T. If you look at this, the fundamental period is T. B is write the Fourier, the integral expression to solve for the Fourier series coefficients. So this would be Cn as per the definition of the Fourier series. We have 1 over the fundamental period, which is t, integral from minus t over 2 to t over 2, f of t, e to the minus j 2 pi n over the fundamental period, which is t times time dt. Okay, and we can further simplify this. This is f of t is a sinusoid, so this would be equal to 1 over t, integral from minus t over 4 actually to t over 4. F of t is sine 2 pi times little t over big T. Then we have e to the minus j 2 pi n over t times time dt. Okay. The last part is find the Fourier series coefficient, simplify as much as possible. So I'll move this out of the way. So it's basically doing this integral, right? And so there's many ways one can do it. There's easier ways and there are hard ways. I generally encourage you to choose the easier way of doing the integral, okay, which is how we did them for the homework problems. You have the sinusoid you can expand using Euler's formula, and then you'll be left with two complex exponentials that multiplies this complex exponential, so you'll be left with kind of two integrals, okay, that you can solve. Before we get there, let's remember. So let's start in part C. Let's remember that something we did at the very beginning of class. Okay, if we have a complex exponential, we integrate about limits symmetric about the origin. We're left with this, which we can then rewrite as we have e to the j omega t naught minus e to the minus j omega t naught over 2j, and then here we have 2 over omega, which is equal to 2 over omega sine of omega t naught. Okay, so let's just remember this. And now we're going to solve for the CNs, but keeping in mind this simple property here. This is equal to 1 over t Now we have e to the j 2 pi little t over big T minus e to the minus j 2 pi little t over big T divided by 2j integral from t over 4 to minus t over 4 times e to the minus j 2 pi n over t times t dt, which is equal to, now let's use these, divide this up into two integrals. We have 1 over t integral from minus t over 4 to t over 4 e to the j 2 pi minus n plus 1 little t over big T dt minus integral from minus t over 4 to t over 4 e to the j 2 pi, so then we have minus n minus 1 little t over big T dt. Okay, I still have this 2j in the denominator. I'm going to bring it out here. Okay. Okay. So then we recognize these integrals as showing up here, right? So the question is, what is omega? Well, omega is whatever is in the exponent, right, multiplying t. Okay, so for the first one, omega is 2 pi times minus n plus 1 over big T. The second one, omega is 2 pi minus n minus 1 divided by big T. Okay, so this is going to leave us with 1 over 2 jt